What if the most terrifying barrier between humanity and the stars isn't distance, but physics itself? Imagine standing beneath a night sky filled with thousands of visible stars. Some are only a few light years away. Others are hundreds, thousands, even millions of light years distant. For centuries, those points of light have looked like destinations, places waiting to be reached. But what if almost every one of them is permanently beyond our reach? Not because our rockets are too weak, not because we haven't invented the right engine, not because civilization hasn't become advanced enough. What if the universe itself has built a wall around us? Leonard Susskind, one of the founders of modern string theory and a major figure in the study of black holes and quantum gravity, has spent much of his career asking a deeper question: what does the fundamental structure of reality actually allow? And when you follow that question into relativity, cosmology, energy, and the geometry of space-time, a disturbing picture begins to emerge. Interstellar travel may not be forbidden in the simple sense that physics says, no spaceship can ever leave Earth. We have already sent spacecraft beyond the planets. In principle, nothing in established physics prevents a human-made object from traveling to another star. The real problem is far more subtle. The universe permits motion. It does not necessarily permit access. And those two things are not the same. The first barrier appeared over a century ago, when Albert Einstein changed our understanding of space and time. Before relativity, it was natural to imagine the universe as an enormous stage. Space was space. Time was time. If you had a powerful enough machine, you could simply cross the distance between two places. Einstein shattered that intuition. According to special relativity, there is a fundamental speed limit built into space-time itself, the speed of light in vacuum, approximately 300,000 kilometers per second. That number is so large that it almost feels meaningless. Light could circle Earth more than 7 times in a single second. A photon leaving the sun reaches Earth in about 8 minutes. So perhaps the answer is obvious. Build a spacecraft capable of traveling close to the speed of light. Then the stars become reachable. But this is where the universe begins to become strange. Suppose you wanted to travel to Proxima Centauri, our nearest known stellar neighbor, roughly 24 light years away. At the speed of light, the journey would take just over 4 years, according to someone watching from Earth. But a massive spaceship cannot actually reach the speed of light. This isn't merely an engineering problem. It is a consequence of relativity. As an object's velocity approaches the speed of light, the energy required to accelerate its mass increases dramatically. The closer you get to light speed, the harder every additional fraction of the speed becomes. You can reach 90% of light speed in principle. You can imagine 99%. You can imagine 999%. But reaching exactly 100% is different. For an object with mass, the required energy would diverge without bound. And suddenly our dream of simply building a faster rocket encounters something much deeper than a technological limitation. There is no known engine powerful enough because the problem isn't the engine. The equations themselves are telling us that a massive object cannot be accelerated to light speed. But here's the first paradox. If you travel extremely close to the speed of light, time for you slows relative to observers who remain behind. This is time dilation, one of the strangest consequences of special relativity. Imagine a spacecraft traveling at 99% of light speed toward another star. From Earth's perspective, the journey could still take years, but for the travelers, the elapsed time can be much shorter. This sounds like a loophole. Perhaps humans don't need to survive centuries-long voyages if relativity lets us cross the galaxy in a few decades of our own time. And this part is real physics. Relativistic time dilation is experimentally confirmed. It isn't science fiction, but it comes with a hidden price: energy. The closer you push your spacecraft toward light speed, the more energy you need, and not just a little more. The increase becomes enormous. At some point, the question stops being, can we build a better rocket? It becomes, can any civilization command enough energy to manipulate matter on this scale? And even if the answer were somehow yes, another problem appears. A spacecraft moving through interstellar space at relativistic speeds would not be traveling through an empty void. The space between stars contains gas, dust, plasma, photons, magnetic fields, and microscopic particles. At ordinary spacecraft speeds, many of these things are manageable. At near light speed, they become something else. A tiny particle of matter encountered at relativistic velocity can carry enormous kinetic energy relative to the spacecraft. A grain of dust can become a high-energy projectile. Radiation becomes increasingly dangerous. Shielding becomes massive. And massive shielding makes the spacecraft heavier, which requires more energy, which requires more fuel, which makes the shielding problem worse. This is the beginning of a brutal engineering feedback loop. But Susskind's way of thinking about physics encourages us to go deeper than engineering, because even if we imagined a civilization capable of solving the energy problem, we would still face the geometry of the universe. And this is where the story becomes genuinely unsettling. The universe is expanding, not simply because galaxies are moving through pre-existing space like bullets flying across a room. The large-scale structure of space itself is changing. Edwin Hubble's observations in the 20th century helped establish that distant galaxies are generally receding from us, with more distant galaxies tending to recede faster. Today, cosmology describes this expansion using general relativity and the mathematics of an evolving space-time. And this creates a bizarre consequence. There are regions of the universe that, because of cosmic expansion, can never send signals to us in the future. Not because they're hiding, not because their engines are too weak, because the structure of space-time prevents communication from ever reaching us. This is the cosmic horizon, and here we encounter an idea that fits naturally into the kinds of questions Susskind has spent decades exploring. The observable universe is not necessarily the entire universe. It is the region from which information has had time to reach us. Beyond that boundary may lie an enormous cosmos that we can never observe directly. But there's an even stranger distinction. Some galaxies we can see today are already beyond our future ability to reach. Their ancient light has reached Earth. We can observe them. We can study their spectra. We can detect their ancient history. But the same universe that allows their light to reach us may prevent any spaceship we launch today from ever reaching them. Think about that. A galaxy can be visible and unreachable. The universe can show you a place that it will never allow you to visit. That is one of the most counterintuitive ideas in modern cosmology. And it means that the phrase, "the universe is enormous," doesn't really capture the problem. The problem isn't simply size. It's causality. Every physical influence has to propagate through space-time according to the rules of relativity. You cannot simply point a ship toward a destination and assume the destination will remain causally accessible forever. The universe is changing while you travel. The road itself is expanding. And in some cases, the road can effectively disappear. Now imagine humanity survives for another 1,000 years. Imagine we build fusion propulsion, antimatter engines, enormous generation ships, autonomous artificial intelligence, or technologies that seem miraculous by today's standards. We might colonize other worlds. We might establish settlements around nearby stars. Perhaps, if the physics and engineering cooperate, we could spread through a substantial portion of the Milky Way. But even then, the galaxy is enormous. The Milky Way is roughly 100,000 light-years across. At a tiny fraction of light speed, crossing it would take far longer than a human lifetime. Even at 10% of light speed, crossing 100,000 light-years would take roughly 1,000,000 years from the perspective of Earth. At relativistic speeds, time dilation changes what the travelers experience, but it doesn't magically erase the enormous energy requirements or the constraints imposed by causality. And there is another problem that science fiction often hides. Acceleration is not free. A human body cannot simply jump from rest to near light speed. Acceleration produces forces. If you accelerate too violently, the human body is damaged or killed. So a realistic relativistic journey requires a carefully controlled acceleration phase followed by an equally careful deceleration phase. And if you need to carry enough fuel to accelerate and decelerate a massive spacecraft, the fuel itself becomes part of the mass you have to accelerate. This is the rocket equation's nightmare. Every kilogram you want to move requires propellant, but the propellant itself must be moved. So you add more propellant. Then you need more propellant to move that propellant, and the problem compounds. This is why chemical rockets are so inefficient for interstellar missions. Chemical energy simply isn't remotely dense enough to make nearby stars easy destinations. Nuclear propulsion could improve the situation dramatically. Fusion could be even more promising. Antimatter offers extraordinary energy density in principle. But none of these technologies currently provide a practical path to sending humans across the galaxy at relativistic speeds. And this distinction matters. Physics does not say that fusion engines are impossible. It does not say antimatter propulsion violates relativity. It does not say a future civilization cannot build faster and more efficient spacecraft. What physics does say is that certain limits are deeply embedded in the structure of reality. The speed of light is one of them. Energy conservation is another. Causality is another. And these limits cannot be negotiated simply by becoming more technologically advanced. This is where Leonard Suskind's broader intellectual framework becomes especially interesting. Susskind has repeatedly emphasized that the universe cannot be understood simply by looking at the objects inside it. You have to understand the underlying rules. Black holes provide one of the most dramatic examples. For a long time, physicists thought black holes were almost entirely defined by their gravitational behavior. But Susskind became one of the central figures in the black hole information debate, arguing against the idea that quantum information could simply disappear behind a black hole horizon. His work helped push physics toward a radical realization. Information may be more fundamental to the universe than our everyday picture of matter suggests. And if information is fundamental, then interstellar travel isn't merely about moving physical objects from one place to another. It's about moving information through space-time. Your body is information. Your memories are information. Your genetic code is information. The arrangement of atoms in a spacecraft is information. For you to travel from Earth to another star, that information must remain physically coherent throughout the journey. The universe does not merely ask, can matter move? It asks whether a particular physical state can be transported through space-time without being destroyed by energy requirements, radiation, collisions, entropy, and time. And this leads us toward one of the most seductive ideas in theoretical physics. What if we don't need to move the entire person? What if we could scan a human being, transmit the information, and reconstruct that person somewhere else? Science fiction has explored this idea for decades. But once again, physics becomes more difficult than fiction. Quantum mechanics places fundamental constraints on what can be copied and transmitted. The no-cloning theorem tells us that an unknown arbitrary quantum state cannot simply be duplicated perfectly. Quantum information can be transferred through processes such as quantum teleportation. But teleportation does not mean beaming a human body through space. It requires entanglement, classical communication, and the destruction of the original quantum state in the transfer process. It doesn't provide faster-than-light travel. It doesn't bypass causality, and it doesn't offer a practical method for transporting a human consciousness across the galaxy. The word teleportation makes the idea sound magical. The physics is anything but magical. It is constrained, and those constraints keep returning us to the same question. Can the universe be cheated? Perhaps through a wormhole. General relativity allows mathematical solutions that resemble tunnels connecting distant regions of space-time. A traversable wormhole, if it could exist and remain stable, might allow a journey between distant locations without crossing the ordinary distance between them in the usual way. This is one of the most fascinating possibilities in theoretical physics. But there is a problem. The existence of a mathematical solution does not mean nature actually builds it. Traversable wormholes appear to require unusual conditions, often involving negative energy or forms of matter and energy that we do not know how to arrange on macroscopic scales. Quantum field theory does allow negative energy densities in certain circumstances, so the idea isn't simply meaningless. But there is currently no evidence that a usable, stable, human-sized traversable wormhole exists. And even if one did, enormous questions about stability, causality, quantum effects, and gravitational backreaction would remain. So wormholes are not a demonstrated escape route. They're a fascinating possibility at the frontier between general relativity and quantum physics. Another idea is even more famous. What if we could bend space-time itself? If space expands, perhaps an advanced civilization could manipulate that expansion. The Alcubierre warp drive concept, proposed in 1994, showed that general relativity permits a mathematical space-time geometry in which space contracts in front of a spacecraft and expands behind it. The spacecraft itself would not locally exceed the speed of light. Instead, space-time would move around it. It sounds like the ultimate loophole. But again, the equations come with a price. The original concept requires exotic energy conditions, and questions remain about whether physically realizable versions could exist at all. There are also profound problems involving energy requirements, stability, quantum effects, and the creation or destruction of horizons. So once again, theoretical possibility is not technological possibility, and technological possibility is not demonstrated physical reality. This distinction is essential. When people say interstellar travel is physically impossible, they often mean something stronger than science actually establishes. We do not have a theorem saying humans can never travel to another star. We already know that unmanned spacecraft can travel beyond our solar system. We know physics permits massive objects to move at arbitrarily high speeds below light speed. We know relativistic travel can dramatically reduce the proper time experienced by travelers. What we do not know is whether a civilization can engineer a practical, survivable, economical system capable of sending humans across interstellar distances. And when we expand the question from the nearest stars to the entire observable universe, the situation becomes much more severe. Cosmological expansion means that there are regions that are causally disconnected from us in a way no engine can overcome. Even infinite technological advancement would not automatically restore causal contact with everything. This may be one of the most humbling lessons of modern cosmology. Technology can overcome many limitations. It cannot simply rewrite the causal structure of space-time. A Stone Age human looking at the moon could not imagine rockets. A medieval astronomer could not imagine radio telescopes. A person living today might be equally incapable of imagining what a civilization 1,000,000 years from now could accomplish. Perhaps they will discover new physics. Perhaps quantum gravity will reveal structures of space-time that we don't yet understand. Perhaps some future theory will show that our current understanding of horizons, energy, or causality is incomplete. Susskind himself has spent decades working in precisely this territory, where our most successful theories begin to collide. String theory attempts to describe fundamental particles in terms of extended objects and seeks a quantum description of gravity. Black hole physics forces quantum mechanics and general relativity into the same conversation. The holographic principle suggests that the information describing a region of space may be encoded in a lower dimensional description associated with its boundary. These ideas are profound, but none currently provides a practical recipe for escaping the speed of light. And that may be the most important point of all. The frontier of physics is not a catalog of loopholes. It is a search for deeper consistency. Maybe the universe is not challenging us to find a faster engine. Maybe it is telling us that our intuition about distance is wrong. Perhaps space is not the fundamental thing we think it is. Perhaps space-time itself emerges from deeper quantum structures. Perhaps what we call distance is connected to information. Perhaps the apparent separation between two places is not fundamental, but something that emerges from a more basic description of reality. These are serious questions at the frontier of theoretical physics. But until such theories produce experimentally supported predictions that overturn our current understanding, relativity remains extraordinarily successful. And under relativity, the universe does something astonishing. It gives us stars, and then quietly tells us that many of them are not destinations. They are memories. We see galaxies because their ancient light has traveled across space for millions or billions of years. When we look into deep space, we're not seeing the universe as it is now. We are seeing the universe as it was. The farther we look, the farther back in time we see. The night sky is therefore not simply a map. It is a record of cosmic history. And perhaps that is why the dream of interstellar travel feels so powerful. We are creatures evolved on one small planet, staring at ancient light from worlds we may never touch. We have built machines that can cross oceans, climb mountains, orbit Earth, land on other worlds, and escape the gravitational grip of our planet. But the deeper we understand the cosmos, the more we discover that there are boundaries no machine has yet crossed. The speed of light, the energy required for relativistic motion, the hazards of interstellar space, the enormous scale of the galaxy, the expansion of the universe, the limits of causality, the mystery of quantum gravity. And beyond all of them, perhaps a question we haven't learned how to ask correctly. Because maybe the ultimate problem with interstellar travel isn't that the stars are too far away. Maybe the problem is that we still don't understand what far away actually means. Leonard Suskind's work repeatedly brings us to that uncomfortable boundary where ordinary intuition stops working. Black holes challenge our understanding of information. Quantum mechanics challenges our understanding of reality. Relativity challenges our understanding of space and time. Cosmology challenges our understanding of what can never be observed. And together, they suggest something profoundly unsettling. The universe may not be a collection of places waiting for us to visit. It may be a causal structure that determines which places can ever become part of our physical future. Humanity may one day reach another star. It may even spread across a portion of the Milky Way. But there could be an enormous cosmic territory forever outside our reach, not because we lack courage, intelligence, or technology, but because reality itself draws a boundary. And if that boundary is fundamental, then the most advanced civilization imaginable would still face it. So when you look at the stars tonight, perhaps don't ask which one humanity will visit first. Ask something stranger. How many of those stars are physically allowed to become part of our future? And how many are destined to remain forever beyond the edge of what the universe will let us touch?